Alright, these are our notes on section 10.2, and it's going to be on logarithms, and we're going to focus on understanding what logs are and how to simplify, evaluate, and solve logarithmic equations. Alright, first thing I want to do is give you a definition of a log, and it's going to be a pretty basic definition for a logarithm. It is the inverse of an exponential function. And we call them a log for short. Alright, now by inverse, that means that we swap the x and the y value. And there's a key relationship we'll get to in a minute, a key idea of how we do that. But before we get there, we need to understand the different parts of a logarithm. A logarithm has three different parts. We have the base, the number expression, whatever we're taking the log of, and then the answer to the log. Okay, so three parts. And we would write that log, usually we use b for the base, of x equals y. And there's a couple of big ideas, a couple rules that we need to remember when we're dealing with logs. And I'm going to divide it on the equal sign here. Things to the left and things to the right. Things on the left have to be positive. Okay? B has to be greater than 0, has to be positive, and it cannot be 1. And x has to be positive also, has to be greater than 0. You cannot take the log of a negative number. Okay, which means eventually we're going to have to test, and when we find variables, if there's an expression in there, you have to go back in and check your answer, because that whole part there, whatever we're taking the log of, can't be negative. The other side, the answer, it's okay to be negative. The y part. Okay? It doesn't have to be. It can be positive. It can be a fraction. It can be decimal. It can be all sorts of things. But it's okay to be negative. The left-hand side has to be positive, though. Right-hand side, it's okay to be negative. Now, the key idea that we're talking about is how to switch between logs and exponential functions. If we've got log base b of x equals y, we can rewrite that as b to the y equals x, or x equals b to the y. They're the same thing, it's just they're on one side and the left side, and on the other one it's on the right side, the b to the y. Doesn't matter which way, but that's how we would rewrite it as an exponential function. To do that, a lot of people use what's called the loop or the curl, whatever you want to call it, but we start at the base, and then we draw a loop or a curl, and we go to the answer, and then to the whatever we're taking the log of. In this case, it's x. So we would start with the base, go to the answer, equals whatever we're taking the log of. And that's how we get that. That's why this loop makes sense for a lot of people. So I've got 4 problems here, and we're going to rewrite them. So if I gave you a log, you're going to rewrite it as an exponential function, or equation, sorry. If I gave you an exponential equation, you're going to rewrite it as a log. And the curl works both ways. So I'm going to show you this first one. We have log base 3 of 9 equals 2. I'm going to use that curl. We started at 3, and then we hit 2, and we went to 9. That's how we would rewrite it. 3 to the second equals 9. And that makes sense. 3 to the second is 9. It equals 9. It works, and that should happen. They should be equal. The second one, same thing happens. I'm not going to draw the curl on this one, but the same idea. We start with the base, which is 10. We go to the answer, equals whatever we're taking the log of. So 10 to the negative second equals 100, which again is true. 10 to the negative second is really 1 over 10 squared. 10 squared is 100, so it's 1 over 100, which is what we got. It works out. Now, all I'm asking you to do is to show me the rewrite part. So you don't have to check this. It's a good way to make sure you've done it right, because they should be equal, but you don't have to show me that part of it. It works the same, this curl, if we go from an exponential equation to a logarithmic. We would start at the 5, which is the base of the exponential. We go to the answer, we come back to the exponent. So it would be log, we started at 5 of 125 equals 3. Same idea. You can use the same curl to get the answer. I'm not going to do that I'm not going to draw the curl on this next one, but I'm going to show you what we would get. It would be log. We would start at the 27, go to the 3, and it equals the exponent, which is 1/3. Okay, same idea. Some of the questions you'll have on your homework for this section will be that basic. It'll just say rewrite. So you need to make sure if you want to use that curl, that's fine, or you need to understand that it goes base, answer or exponent equals whatever you're taking the log of. Next thing I want to point out is the difference between solve and evaluate. Now this is something we've done before. I just want to make sure we understand the difference. Solve will have an equal sign. Okay? Has to have an equal sign. It'll be some sort of equation where we're working towards getting x equals a number or y equals a number, equals a value. Evaluate is just going to be an expression. And we're going to simplify that expression so we get down to one number. The difference, you have to know the difference between the directions, and when we do these evaluate problems, we're actually going to make an equation, but we're not going to write them as x equals. So I've got 4 examples here. We've got and we're going to evaluate them, which means we're just going to simplify them. First one is log base 3 of 243, and we want to figure out what that would be as an answer. To figure that out, we're going to go ahead and make it an equation. We're going to set it equal to x, and we're just going to solve for that variable x. So we're going to use that curl. It would be 3 to the x power equals 243. Now we've solved problems like this before. We need to figure out what 243 would be as 3 to some exponent. And then when we get that, we can cross our bases out, and then x is going to be the answer. So what we need to do is figure out what 243 is going to be rewritten as 3 to some exponent. Now you do have that exponent chart I gave you back in chapter 5 that would be helpful. You don't have to use it, or you can just put it in your calculator. Either way, it's going to work the same. You can do it through trial and error. Okay, 3 to the 5th is actually going to be 243. So we've got 3 to the x equals 3 to the 5th. Cross out our 3's. X is 5. We're evaluating this. It's not an equation. We added that x into the problem, so we don't want to have it for our answer. The answer to the problem is just going to be 5. Okay? Let's look at another one. Let's look at this one over here. Log base 5 of 0.2. We want to set it up so that it equals x, and we're going to use that curl. So we have 5 to the x equals 0.2. Now 0.2, we're going to rewrite it as a fraction because that doesn't really help us. 0.2 is really 1/5. And we're going to use an idea we used in the last section in 10.1. That's a fraction. We could make it 5 to the negative 1 because it's under 1. So we have 5 to the x equals 5 to the negative 1. We cross those bases out, which is going to be x equals negative 1. We made it an equation. We don't want to do that. We're evaluating. We don't need to have x equals, so the answer is just going to be negative 1. The next one, log base 2 of 64. We're going to set it equal to x. I'm going to let you pause this and see if you can come up with the answer for both of these next two. Log base 2 of 64 and log base 10 of 10,000. Go ahead and pause this, see if you can come up with the answers, and then come back and check them. Alright, let's look at these real quick. We would have 2 to the x equals 64. 64, we need to rewrite that as something squared. It's going to be 2 to the 6th. 2 to the x, cross out your bases. It would really be x equals 6, but since we added that x to the problem, the answer is just 6. For the second one, we have 10 to the x equals 10,000. 10 to the x, 10,000 is really 10 to the 4th. Cross out your bases. Answer is going to be 4. Okay, let's move on. Now I'm going to show you a shortcut, and this is a different way to solve these problems. Alright, if we've got log base 9 of 9 squared, where we have an exponent and what we're taking the log of, and our base and the base of what we've got the exponent on are the same, what happens is that they just cancel each other out. Now this makes sense because we could set that equal to x. Let's rewrite it. Log base 9 of 9 squared equals x. If we rewrote that using the loop, it would be 9 to the x equals 9 squared. 9's just cancel, answer's 2. Instead of going through all that rewriting stuff, we can just cancel it out at the beginning, and we know the answer is going to be 2. So let's look at this one. Log base 7 of 7 to the 5th. Goodbye to the 7's in the log, answer's 5. The next one, log base 2 of 2 to the negative 16. Cross it out, answer's negative 16. Now this next one is a little different. Log base 4 of 64. 64 is not the same base. It's not something to the exponent, but we could rewrite it as log base 4 of 4 cubed, because 4 cubed is really 64. When we do that, bases are the same. Answer's 3. Okay? That's a key idea. That will save you some time. And we could have used that on those other 4 problems we just did. We could rewrite them so that they have a base that's the same as the base on our log. Just cancel it out. Give the exponent as the answer. I want to point this one out. This is the same idea. Okay? It's just written differently. Instead of having the log with the small base, the base on our log, and then an exponent with a base, it's backwards. We have a log in our exponent. Same thing happens though, is that these just cancel because they're both the same, 7 and 7. And then this would be the answer to our problem, x squared minus 1. Those are a little trickier, but the same idea happens. Okay, same bases, base in the exponent, base in the log, cancel each other out, and whatever's left is the answer. We're going to move on now, and we're going to solve some problems. We're going to solve them the same way we did the other ones. The difference is it's got an equal sign in it. So when we give our answer, it's going to be x equals, n equals, b equals, whatever we have in the problem. So let's go ahead and use that curl. We have log base 10 of n equals negative 3. When we use that curl, we get 10 to the negative third equals n. 10 to the negative third be n equals 1 over 10 to the positive third, and 10 to the positive third is 1,000. So n equals 1 over 1,000. There's our answer. Notice we wrote the answer n equals this time because it had an equals in the problem. We didn't add that to it like we did with the evaluate ones. Let's go to the next one. We have b to the 5th. Well, that's what we get when we write it. We have log base b of 1,024 equals 5. So we have b to the 5th equals 1,024. And this is kind of a new idea. We haven't seen this before. We don't know what the base is. We know the exponent. We're going to use that same idea we do when we have, we want to get the same base, but this time we want to get the same exponent. So we want to rewrite 1,024 as something to the 5th power. So if we have that exponent chart from chapter 5, this would be a good idea to use, a good place to use it, because we could just go down the 5th column and find where we get 1,024. When we do that, we notice that it's 4. 4 to the 5th is 1,024. Now what happens is that since our exponents are the same, the bases have to be the same too. So the answer here is b equals 4. I'm going to let you try these next two. We're going to make them pause and practice problems. You can pause the pencast, see if you can come up with the answer, and then come back and check them and make sure you got the right answer. So go ahead and pause them and solve these, please. Alright, answer to the next problem. Log base 4 of x equals 3 halves. Rewrite it. So 4 to the 3 halves equals x. And you can just put that in your calculator. 4 to the 3 halves. 4 exponent, put your 3 halves in parentheses. When we do that, we get 8. There's the answer. Next one. Y, or log base y of 16 equals negative 4 would be y to the negative 4 equals 16. This one's trickier because we have a negative exponent here on the y. We want to make that positive, so let's make it 1 over y to the 4th equals 16. I'm going to make that 16 over 1 because now we have a proportion and we could cross multiply. I'm going to divide both sides by 16. Y to the 4th equals 1 over 16. Let's take the 4th root of both sides. I'm running out of room, so we're going to jump back up. 4th root of 1 over 16, that would be the fourth root of 1 over the fourth root of 16. Fourth root of 1 is 1. Fourth root of 16 is 2. So there's our answer, 1/2. That one's tricky. It's got more steps to it. You will see that again, so make sure if you have questions on this when you ask them in class, I'll be more than happy to give you another example. You just need to ask. Alright, those are pretty basic ones. We're going to move on to a couple equations here that are a little different. Notice that we have expressions with our logs. And these ones we just did is just a variable. It's just one variable there. Here we have a set of parentheses with an expression on the inside. When that happens, we need to make sure we check the answer. Okay? Because we always want to make sure that we're taking the log of a positive number. And when we're solving for a variable here, when we plug it back in, it may be a positive, it may be a negative when we actually simplify it out. So we want to make sure we check our answers on these. We're going to solve them the same way, though. We have log base 6 of the quantity 2y plus 8 equals 2. So we're still going to use that curl. It means 6 squared equals 2y plus 8. Well, 6 squared is 36 equals 2y plus 8 minus 8. 36 minus 8, well, that is 24 equals 2. I lied, it is not 24, it's 28. That was my mistake. Divide both sides by 2. Y equals 28 divided by 2 is 14. So there would be our answer. Now, before we actually say it's the answer, we need to check it. Okay, we're going to go back to the original problem. We're going to plug it in for what's in the parentheses here. 2 times 14 plus 8. And we just want to make sure that that's positive because we can't take the log of a negative. Well, 2 times 14, that's 28, plus 8 is 36. 36 is a positive number. Okay, so it works out. So there is the answer, y equals 14. We're going to use that same idea on this next one. Log base 7 of 8x plus 20 equals log base 7 of x plus 6. Now notice we have logs on both sides. We're going to go ahead and rewrite that using this curl. So 7, and then everything on this side of the equal side, log base 7 of x plus 6 equals 8x plus 20. Now we've seen this right-hand side before. We have 7 log base 7. Same bases, they cancel out. So we end up getting x plus 6 equals 8x plus 20. Notice that all that really happened is that we crossed those logs out at the beginning. They've switched sides, the x plus 6 and the 8x plus 20, but that doesn't matter in the long run because we're going to be solving it the same way. So at the beginning, all we could have done, if that base is the same for both logs on both sides, we just can cancel it out. And we're going to use that on this next example. Well, let's finish solving this one first. We've got x plus 6 equals 8x plus 20. Subtract x from both sides. At the same time, I'm going to subtract 20 from both sides. You can do it in 2 steps if you need to. 6 minus 20, well, that is negative 14 equals 8x minus x is going to be 7x. Divide both sides by 7. X is negative 2. Now we want to go back and we want to make sure that that's positive, and we're going to have to check both sides to make sure that the quantities in the parentheses are positive. So 8 times negative 2 plus 20, that's negative 16 plus 20, which is 4. Good, that one works. That's still positive. The other side, negative 2 plus 6, well, that's 4. It's positive also. So it does work. That's the answer to the problem. One more example like this. Okay. Notice again, we have the same log with the base on both sides. We just talked about that with this last example. Same base, goodbye, they cancel each other out. So we get x squared minus 2 equals x. Let's take that x to the other side. X squared minus x minus 2 equals 0. This should look familiar. It's a little different from what we've seen so far in this chapter, but we've seen this before. We have 3 terms. One of them is squared, and it's equal to 0. Should trigger something in your brain. We're going to x factor this, because there's 3 terms. So we have negative 2 on top, negative 1 on the bottom. We want 2 numbers that multiply to negative 2, but add to negative 1. Alright, so we need to come up with numbers that multiply to negative 2, add to negative 1. Pretty easy numbers to come up with. Negative 2, positive 1. Those two multiply to negative 2, but they add to negative 1. Now we can use our shortcut because a is 1, so we end up with x minus 2 equals 0, x plus 1 equals 0. We're going to solve for x in both of those, so x equals 2, x equals negative 1. Now in this case we have two answers to check for. We want to make sure that both of them work in the problem. And remember, we can't take the log of a negative. I'm going to use this side here first because it's going to rule out one of the answers already. Negative 1. Log base 3 of negative 1. That's not going to work. That one is gone because we can't take the log of a negative. 2 still works though. And if we plug it into the right hand side, 2 is okay. The left hand side would be 2 squared minus 2. Well, 2 squared is 4. 4 minus 2 is 2. That's still positive. So this answer does work. So of the two that we got, only one of them works because we remember we have to go back and check them. Alright, we're going to look at one other quick thing. We've solved equations. Now we're going to go and we're going to solve inequalities. Now, for an inequality, it's basically the same thing. The difference is that when you rewrite them, depending on whether it's a greater than or a less than sign, there's a rule on how to rewrite them. But we solve everything else the same. Alright, so this first part here, it's basically going to be the same for all of them. If b is greater than 1, that has to be true. The base has to be positive and it can't be 1. And x is greater than 0 because we can't take the log of a negative. And we have log base b of x is greater than y. Then we rewrite it so that x is greater than b to the y power. And it's going to be written this way. It's important that you write it this way, that what we're taking the log of is greater than b to the y, and then we would solve it from there. We're going to skip down real quick. We're going to do this example here because this is an example with a greater than sign. So we've got log base 6 of x is greater than 3. We want to check and make sure everything's the same. X is what we're solving for. We want to make sure in the end that it's greater than 0. That's good. And b is greater than 1. b is 6. So we're going to rewrite it. It would be x is greater than 6 to the third. So x is greater than 6 to the third is 216. Now to check that, we just want to make sure that all of these x's, when we plug them in, they are greater than 0. Well, anything greater than 216 is going to be greater than 0, so it does meet the requirements, and there would be the answer to our problem. We're going to jump back now, and we're going to use the second one. Okay, the second one is for a less than. If b is greater than 1 and x is greater than 0, that's what we want to see. And log base b of x is less than y, then we rewrite it so that it is 0 is less than x is less than b to the y. So it's sandwiched between b to the y and 0. So jump to the second example. Log base 3 of 2x minus 1 is less than or equal to 2. Now notice the one difference is that we've got an equal to here. That's okay. It can be less than, greater than, or equal to. It's not going to change how we rewrite it. But we do have a variable we're solving for, and it's a less than sign, so we're going to sandwich it between 0, the 2x minus 1, and then 3 squared, because that would be our base and our answer. Well, 3 squared is really 9, so we have 2x minus 1 sandwiched between 0 and 9. Now we're going to solve that. We're going to add 1 to all 3 parts. We've done this way back in chapter 1, so this may be a review. It's just like solving an equation, except we got to go to all 3 parts. That cancels this, so we have 1 is less than or equal to 2x is less than or equal to 9 plus 1 is 10. We're going to divide all 3 parts by 2. Gives us 1/2 is less than or equal to x. It's less than or equal to 10 divided by 2 is 5. Now again, you want to go back and check. You want to make sure that your x's are positive. Well, if we plug anything in this range from 1/2 to 5 in, we're going to get a good answer. Okay? So it's all right. When we plug 1/2 in, if we think about it, 2 times 1/2 is 1. 1 minus 1 is 0. That's okay. We can take the log of 0. It just can't be negative. And then 5, if we plug 5 in, 2 times 5 is 10, minus 1 is 9. 9 is positive, so it works also. So anything in that range is going to work, which is good. That's what we want to see. We want to make sure that it works in our problem. We can't take the log of a negative. And then those are all of our notes. Now, I realize that's a lot. This is a pretty long video. I apologize for that. But it's basically the same thing over and over again. We're just rewriting using that key idea where the base, the answer, and then the exponent, or what we're taking the log of, sorry. That key idea is important. You have to remember that. These equations, we solve them a little differently, and the inequalities, but it's that same key idea over and over again. So bring any questions you have to class, and we will go over them. I anticipate questions on the inequalities and perhaps the equations, but other than that, you should be good to go. Again, bring questions if you have them, and these are our notes on section 10.2 on understanding logs.